If the result of applying operator A on a specific function f gives back f multiplied by some constant c, then we can say that the function f is an eigenfunction of operator A, and the constant is an eigenvalue. Please note that this expression you see here, a hat f equals c times f, is not a definition of what operator A does. Here, f is not an arbitrary function. The function f that we are referring to in this expression is one that specifically yields a constant times itself if operator A were applied to it. In general, operators may have more than one eigenfunction, each with a different eigenvalue. Suppose operator D is defined such that applying it on a function yields the derivative of the function with respect to x. Is e to the kx, where k is a constant, an eigenfunction of operator D? To answer this question, we just apply operator D on e to the kx. We find that it is equal to k times e to the kx. Is this equal to a constant times the original function? The answer is yes. The constant is k. So we say that e to the kx is an eigenfunction of operator D with an eigenvalue equal to k. In case you need a math review, we use the chain rule to take the derivative of e to the kx with respect to x. Recall that the derivative of e to the x with respect to x is equal to e to the x. Here, x can be anything. So we can say that the derivative of e to the u with respect to u is equal to e to the u. But what we want is the derivative of e to the kx with respect to x, not x with respect to x. It's not quite the same. So we make a substitution. We let u be equal to kx, which means that our function f, which is equal to e to the kx, can now be written as e to the u. And we can say that the derivative of f with respect to u is the derivative of e to the u with respect to u and is equal to e to the u. Now we apply the chain rule. The derivative of f with respect to x is equal to the derivative of f with respect to u multiplied by the derivative of u with respect to x. The chain rule is easy to remember. Think of this du and this du as canceling each other out. That leaves this df divided by this dx, which is what we want. We already know the derivative of f with respect to u. It's e to the u. The derivative of u with respect to x is simple. Since u is equal to kx, the derivative of u with respect to x is just k. Finally, we substitute kx back in for u. We get e to the kx times k, or k times e to the kx. Suppose operator D is defined such that applying it on a function yields the derivative of the function with respect to x. Is sine of kx, where k is a constant, an eigenfunction of operator D? To answer this question, we just apply operator D on sine kx. We find that it is equal to k times cosine kx. Can we write k times cosine kx as a constant times sine of kx? The answer is no. Therefore, sine of kx is not an eigenfunction of operator D. Is 2x squared an eigenfunction of the parity operator? The parity operator is defined such that when applied to a function of x, we just replace every occurrence of x by negative x. Let's apply the parity operator on 2x squared. Replacing x by negative x, then squaring, gives back 2x squared, which we can write as 1 times the 2x squared. Therefore, we say that 2x squared is an eigenfunction of the parity operator with an eigenvalue of 1. In general, even functions, for which f of negative x is equal to f of x, are eigenfunctions of the parity operator with an eigenvalue of 1. What about odd functions? They are also eigenfunctions of the parity operator, but with an eigenvalue of -1. Eigenfunctions of an operator that have the same eigenvalues are said to be degenerate. In the example shown here, which eigenfunctions are degenerate? Functions f2 and f3 have the same eigenvalue. The eigenvalue is 4. Therefore, they are degenerate. Any linear combination of degenerate eigenfunctions of a linear operator is also an eigenfunction with the same eigenvalue. Here's the proof. Let functions f1 and f2 be degenerate eigenfunctions of operator A. This means that operator A applied on function f1 yields c times f1, where the constant c is the eigenvalue. Similarly, a hat f2 is equal to c times f2. In both cases, the eigenvalue is the same because f1 and f2 are degenerate. Let's apply operator A on a linear combination of f1 and f2. The linear combination of f1 and f2 is c1 times f1 plus c2 times f2, where c1 and c2 are constants. Since A is a linear operator, we can distribute it to the two terms and pull out the constants. This gives us c1 a hat f1 plus c2 a hat f2. If we apply the operator on functions f1 and f2, we get c1 times c times f1 plus c2 times c times f2. We can factor out c and get c times the linear combination c1f1 plus c2f2. In other words, applying operator A on the linear combination c1f1 plus c2f2 gives us back the same eigenvalue c times the linear combination. What if we take a linear combination of non-degenerate eigenfunctions? Will it also be an eigenfunction? The answer is no, because they won't have a common eigenvalue that we can factor out in the last step. Consider the integral shown here, where operator A is first applied on some function g. So g is transformed into another function, which we emphasize by putting a hat g in parentheses. Then we multiply the function with the complex conjugate of another function, shown here as f, and we integrate over all space. This type of integral is quite common in quantum mechanics and is often abbreviated using the Dirac bracket notation, which look like these. We can think of the Dirac bracket notation shown here as the application of a product of three operators on function g. In the example shown here, the rightmost operator, which is first applied, is called the ket operator. Instead of representing the operator using a letter with a hat, we just enclose the function by a bar and a greater than sign. The ket operator does nothing to the function it is applied on. It is an identity or do-nothing operator. Ket applied on g just gives g. Ket applied on a hat g just gives a hat g. The second operator is operator A. Note that it can be merged with the ket operator by removing the bar from the ket operator. We say that we can just insert the second operator into the ket operator. This is because an identity operator, which is what a ket operator is, commutes with any operator. Finally, the leftmost operator, which is applied last, is the bra operator. The bra operator has a function specified between a less than sign and a bar. The rule for the bra operator is that if we apply it to a function, then we must first multiply that function by the complex conjugate of the function specified in the bra operator, then integrate over all space. Note that we do not put an asterisk on f inside the bra. The complex conjugate is implied by putting it inside the bra. Note that it is also customary to put a closing bracket, a greater than sign, after the function that we apply the bra operator on. An operator A is said to be Hermitian if, for any pair of arbitrary well-behaved functions f and g, the equation shown here is true. Let's examine this equation carefully. On the left side, we have an integral where operator A is applied on an arbitrary function g. Then the resulting function is multiplied by the complex conjugate of arbitrary function f. Then integration is done over all space. The equation says that we get the same result if we switch f and g and we take the complex conjugate of the integral. The right-hand side of this equation can be rewritten several ways. All of these ways are equal whether A is Hermitian or not, but they are only equal to the left-hand side if A is Hermitian. Let's take a look at these equivalent ways of writing the right-hand side. First, we can get rid of the outermost complex conjugation by replacing g star inside the integral by g star star, or simply g. If we get rid of the outermost complex conjugation, we must also take the complex conjugate of a hat f inside the integral. Here's the same equation written in Dirac bracket notation. If operator A is Hermitian, then we can switch the functions in the bra and ket, but we must take the complex conjugate after the switch. These three expressions on the right-hand side are equivalent whether or not A is Hermitian. They are equal to the left-hand side only if A is Hermitian. This is the bracket notation for these, and these are the bracket notation for this. If operator A yields the derivative of the function it is applied on, is it Hermitian? Let's apply A on an arbitrary function g, multiply by the complex conjugate of arbitrary function f, and integrate over all space, which in this case is from x equals negative infinity to x equals positive infinity. Based on the definition, we can replace a hat g by the derivative of g with respect to x. We use a technique known as integration by parts. We let u equal to f star and dv equal to the derivative of g with respect to x times dx. Then du is the derivative of f star with respect to x times dx. And v is equal to g. This is the integral of u dv, and it should be equal to u times v minus integral of v du. F star times g is evaluated from negative infinity to infinity. Since the functions are well behaved, the functions go to 0 at infinity and at negative infinity. So f star times g evaluated from negative infinity to positive infinity is equal to 0. That leaves the negative of the complex conjugate of the integral of g star times a hat f dx. This is the negative of what we would expect if A were a Hermitian operator. Because of this negative sign, we conclude that an operator that yields the derivative of a function is not a Hermitian operator. In Dirac notation, we have just shown that bracket f a hat g is equal to the negative of bracket g a hat f star, which means that A is not Hermitian. Consider the integral represented by bracket f a hat g. If we can show that an equivalent integral is obtained by moving the operator in front of the function in the bra, then the operator is Hermitian. If a hat yields the derivative of a function, we have shown that the operator is not Hermitian because moving the operator in front of the function in the bra gives us an integral that is the negative of what we would expect for a Hermitian operator. However, we can show that the square of operator A is Hermitian. Here's how. We write bracket f a hat squared g, then show that we get an equivalent integral if we move the a squared operator in front of the function in the bra. The first thing we need to do is apply the right a hat to g. This leaves just one a hat operator in the middle. We have already seen that we can move it in front of the function in the bra, but we need to change the sign of the integral. Now we take the a hat in the ket and move it back to the middle. Then we can see that we can move it in front of a hat f in the bra and change the algebraic sign again. Thus, a squared is a Hermitian operator.